So just like any other scientist that we've studied, Bohr's model was actually proven incorrect, that it's not a good representation of how electrons are organized. So just like Dalton was proven wrong by Thomson, who discovered subatomic particles, when Dalton had said, well, the atom is indestructible, you can't divide it any smaller. Just like Thomson had said, oh, well, the atom is made up of positive charges throughout, the plum pudding model, and Rutherford said, no, 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 it's the nucleus, a dense, small center. And Rutherford was then proven wrong, I guess, by Bohr, who came up with the concept of discrete energy levels in which the electrons orbited around the nucleus. Bohr was proven wrong, and specifically, Bohr was proven wrong, yet he provides us with important information. So the first thing that he came up with was the concept of energy levels. And so we will still use this concept of energy levels, n equals 1, n equals 2, n equals 3. And the other idea that he came up with was the fact that energy is quantized. There are specific quantities of energy that will be released and that will be absorbed by electrons in order to move from one energy level to another. So each of these scientists came up with a concept that's extremely important for us, but we're going to move on from Bohr now, this concept of orbiting, and we're going to come across orbitals. Now, an orbital is a 3D volume where electrons have the highest probability of being found. Now, this is like saying a little bit slow. This is like talking about me in my classroom. Now, I won't always be in my classroom. However, if we talk about, let's say, as your book says, 100-meter radius, most of the time you will find me within that radius. Now, not all the time. I might go to the teacher's lounge, I might go to 402, I might go to some other classroom. However, the majority of the time you're going to find me within 100-meter radius of my classroom. So that is what an orbital is, but in a 3D sense. Now, we have got 4 sublevels that we're going to talk about. We've got this S sublevel, which you can see looks like a sphere. Okay. We've got this P sublevel. We call these dumbbells. Now, the dumbbell can be in the X axis, as you can see here. It can be along the Y axis, and it can be along the Z axis, because we're talking about a 3D shape. So this combined, when you combine all of those, this is what the P sublevel looks like. The D sublevel is kind of crazy, and you can see what it looks like. Now, I wouldn't expect you to memorize these shapes. Now, these all represent orbitals, the locations where electrons are most likely going to be found. And so what I'm going to show you really quickly is a YouTube video that actually shows you this, and I'll give you a little bit more of an explanation while I show this. Alright, so this is the 1s orbital. It's the sphere, just like how I explained before. The interesting thing is, if you notice, you've got before it was 1s. The 1 represents the energy level, and so this is a pretty small sphere. When you get to 2s, the second energy level, so we're still using Bohr's energy levels, we've got a much larger sphere, okay, much larger sphere. It's still the exact same shape, except the electrons can occupy a much greater space. And remember, the farther away you get from the nucleus, the more energy the electrons will have. And so the 2s orbital, because the electrons can be farther away, they will have more energy. And remember, this is still the probability, the most likely place where the electrons will be found. Yeah, sure, there can still be electrons that are found elsewhere, but just keep in mind it's the idea that Ms. Polliner's normally in her classroom within a certain radius. Same thing with the orbital. Now, we're going to get to P now. The p orbital doesn't start until the second energy level, but when it does, if you notice, here we've got the p orbital along the x-axis. It's nice and big. And then we're going to have the p orbital around the y-axis. You can see it right there. And then you have the p orbital along the z-axis. axis. So all of this is showing you is the most likely place where you're going to find the electrons. And what you should come away with this, concept-wise, is the fact, and it looks really, really cool, this is not the normal idea that we have about electrons, the traditional orbiting around like what Bohr came up with. Instead, it's regions, and funky-looking regions, but still regions where your electrons are most likely going to be found. All right, so I'm going to get back to our notes, all right, and explain a couple more things to you. First of all, each orbital, each sublevel, can fit a maximum number of electrons, and I'll show you how the periodic table is awesome with regards to this in just a second. So for your S sublevel, it can only fit 2 electrons. For the P orbital, it can fit 6. For the D orbital, it can fit 10, and there's actually one more sublevel, which I didn't include because you're not responsible for the shape. But the F sublevel, and I'm just going to write F sub, the F sublevel can fit a total of 14 electrons. Now, how do we know which orbital the electrons are going to fill? Well, they fill it in order. They fill it, the electrons first fill the lowest energy level, and then they move up. They occupy the lowest energy sublevel, the S, and then the P. And I'll show you how the periodic table actually enables you to anticipate which orbitals will be filled. It's really, really, really cool. So I'm going to show you how you can actually use the periodic table to figure out how the electrons are organized for a specific atom. So each orbital has its specific block. So this is the S block right here, and I'll show you why this is so cool in just one second. So I'm going to highlight it. You can highlight it in your notes. Don't highlight all the boxes because we're going to fill those boxes in. So I'm just going to go like that. This is my S block. Now I also need to include, notice there's a missing piece. I also need to include helium over here. That's my S block. Now, why is this so cool, Ms. Pollner? Well, as we had said previously, the S orbital can fit only 2 electrons in one specific sublevel, one S orbital. Now, if you look, you've got 1, 2 blocks right there. That represents 1, 2 electrons. Now, for the P block, I'm going to highlight this over here. This is your P block over here. Now, remember from our notes that the P block can fit 6 electrons, so let's confirm that. 1, 2, 3, 4, 5, 6. That's super cool. Now, let's look at your D block. Well, your D block is your center with your transition metals. So we'll highlight this. Highlight this. There's your D block. And remember, your D block can fit 10 electrons. Let's count it. Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Awesome. The only one that's missing is your F block. Well, your F block is right here at the bottom. Your inner transition metals, remember the ones that technically are supposed to go within your transition metals right here, but because you don't want your periodic table to be super long and awkward, you just put it on the bottom. All right. The F block can fit 14 electrons. Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's awesome. Now, here's how we will write what we call our electron configuration. Your electron configuration is just the manner in which the organization of your electrons, how they are organized around your nucleus. Okay, so we're going to start off. We've got our S block. Each of these rows represents an energy level. So this first row is n equals 1. This second row is n equals 2, etc., etc. So right here, you're in your first energy level, you're in the S orbital, and you've only added 1 electron so far. So this is a superscript right here. So this is 1s1. I'm going to move over right here. There's going to be a lot of writing in this, guys, but it's going to help you a lot, I promise. Still in the first energy level, still in the S orbital, but you now have 2 electrons. Now I'm going to move down here. I'm in the second energy level, still in the S orbital, but now I've only got one electron in this sub-level. So I'm going to restart it and put a 1 there because I've only got one electron in the 2s. Here, second energy level, S sub-level, now I've got 2 electrons. Notice I'm kind of reading it across like a book. Here, I'm in the second energy level. I'm in the p orbital now, so I've got to restart my number of electrons again. So this is going to be a 1. Here, second energy level, p sub-level, 2 electrons. Second energy level, p orbital, 3 electrons. Second energy level, p orbital, 4 electrons. And I'm going to keep going across. And if you guys see the trend and you want to go ahead of me, go for it. That's totally fine. You can fast forward me. Be careful, so 2p6. Be careful with the D and the F because there are exceptions. So maybe don't go too far ahead. 3s1. Third energy level, s orbital, 2 electrons. 3p, 1 electron, first electron in this sublevel. 3p2, 3p3. I'm going to start writing a little bit faster. All right, I'm going to go here, fourth energy level, S1, 4s2. Now, what you would anticipate for the D would be for this to be 4D, but it's not. It's actually 3D. So that's the first exception. The reason why, I'm going to explain as I write, the reason why, as we move across the way that I'm writing this, we're going in order of increasing energy, right? So 1s has the lowest energy of all of these, then 2s, then 2p, then 3s, then 3p, and interestingly, after 4s, the next energy level, the next sublevel, sorry, that has the next highest energy is the 3D, not the 4D. So, I skipped. 1, 2, oops, 3, I can't talk while I write. 4, 5, 6, and 7. So 3D 8, 3D 9, 3D 10. All right, then I go back to my 4. So 4p1, because 4p has more energy than the 3D. So I'm going to cheat a little bit. I'm just going to fill this in quickly at this point because I'm hoping you guys get the picture. So I'm going to stop talking. For F's, this row is going to go in right there. It's going to cut in between the 6s and the 5D. Okay? This is going to cut in between the 7 and the 6D. So here, F, you would expect it to either start with a 6 or a 5. Well, no, unfortunately, it starts with a 4. So you got 4F1, 4F2, all the way across. All right, for the next row, it starts with 5. So 5F1, F. Sorry, guys. My letters are getting bad as my hand starts to hurt. You can fast forward me if you're done. Now, probably what's going through your head as you're writing this, how in the world am I going to use this? Well, this is going to show you, this is going to help a lot, that's a 9, in creating your electron configuration. What your electron configuration is identifying where exactly each electron, well, not exactly, but approximating where your electrons are, going to be located. All right, so in what orbital will you most likely find them? Which principal, which energy level, where are you most likely going to find them, etc., etc. Sorry guys, my handwriting has gotten worse and worse. All right. Whew, I'm done. I'm going to show you, I'm going to write the electron configuration for this first element. So this is phosphorus. So obviously I don't have the names of the elements on this because I've taken the time to write out each electron configuration. So phosphorus is actually going to be located right here. All right. So what we're going to do, I'm going to write out the electron configuration. To write out the electron configuration, guys, it's like you're reading a book. All right. So I could write this as follows. I could write 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3. That's a lot to write. So instead what you can do is you can say, okay, if I'm at 1s2, that implies that I have 2 electrons already. I have my 1s1 and I now have 1s2. So I have 2 electrons. So I'm going to start off. I've got 1s2 because I've gotten through here. I'm going to want to include this as well, these 2. So it's going to be 2s2. I'm going to want to include all of these, so I'm going to go all the way to 2p6. I'm going to want to include all of these 2, so 3s2. And then I'm going to want to go just to 3p3. Now, good news and bad news. Good news, on a quiz or test, I will give you a periodic table. Bad news, I will not give you this handy-dandy table. However, at a certain point, you're going to get so comfortable with writing these, with the S block, the P block, the D block, the F block, it's going to be kind of second nature, and you'll just count across 1, 2, 3 to get 3p3. All right? I'm going to give another example. I didn't provide this in your workbook, but just if you want more help, awesome, use it. If you don't, then please get rid of me, and I just need you to complete the electron configuration of manganese and silicon, so just number 1 and number 2. So you can leave me if you want to. I'm going to go to right here, and this element is actually germanium. All right, so I'm going to write the electron configuration for Ge. All right, so I've got 1s2, so I'm going to write that right here, 1s2. Then I've got 2s2. Then I want all of these p's, so it's going to be 2p6. Then it's going to be 3s2. I want to include all of these p's, so 3p6. I'm going to go down here, 4s2, because I want to include all the 4s's. I want to include all of the d's, so 3d10. And then I stop at 4p2. So what this is showing you, there are 2 electrons in the 1s orbital, there are 2 electrons in the 2s orbital. In the 2p, there are 6 electrons that will most likely be found there. In the 3s, there are 2 electrons, etc., etc. So this is showing you not like, oh, in my Bohr model, like these are going to be orbiting around my nucleus. Instead, this is much more complex in the sense that it's showing you the volume, the shape where you will most likely find your electrons, and also the energy level is showing you the size of that orbital. And that's it.